In previous lectures, we've learned how to study the results of a single sample, whether it's a single poll or a single medical result or a single study of human body temperatures or a single study of those skeletons. We had one sample and we tried to do inferences on it. That could involve getting a confidence interval or it could involve doing a hypothesis test. But we always just had one sample to consider. Or most recently, we talked about having paired samples where really we can just look at the difference between everybody's result in the second sample minus the first sample, and then it pretty much reduces to just having one sample. Now we're going to consider the case where we have two independent samples. So we have one sample about a certain result or fact, and then we have a whole other sample. And the question is, what can we do to infer between them in that case? For example, maybe we had one poll of a politician's support at one time, and then a few months later we had a second poll, and we want to make inferences about how the support for that politician has changed. So how can we do that? Well, to start off, let's remember what we did in the one sample case. And in particular, if we just had one proportion with some sample size n, and some observed fraction of successes or support or whatever, which we call p hat, then we knew some theory. We developed using the central limit theorem the idea that p hat minus p approximately had a standard normal distribution, and we knew the mean and we knew the variance. And this was good because we could use this fact to approximately compute confidence intervals and approximately get the p-values for hypothesis tests. So for one sample, we understood all that. Now suppose we have two independent samples, and let's say they're each a proportion, like they're two different polls, but they're done independently. So it's not asking the same people again and seeing how they've changed. It's asking one sample and then later asking a whole different sample. There's no matching involved. We have two different proportions. So in this case, the first sample might have been of size n1 and the second one of size n2, and they could be different sizes. And in any case, we would probably observe different fractions of successes, a p1 hat and p2 hat. And what we're interested in are things about the difference between p1 and p2. Well, we can just look at the difference between the two samples. That's p1 hat minus p2 hat. And of course, the mean of that will still be p1 minus p2 because the mean of p1 hat is p1 and the mean of p2 hat is p2. So that's good. We already have a statistic which has the right mean. But in order to make progress with things like confidence intervals and hypothesis tests, we need to also know things like the variance. Well, we can work that out too. So in this case, the variance of p1 hat minus p2 hat, well, first of all, that's kind of like a variance of a sum of two things, but then one of them had a minus sign, but that's okay because variances get multiplied by the constant squared. So since they're independent, we can add the variances, and since we get to square it, that minus 1 squared kind of goes away. And we just have a sum of the two individual variances, which is that old formula that we remember for the variance of a proportion, the p times 1 minus p over n. Well, now we've got a sum of two of them. Okay, now if the two samples are reasonably large size, then it's still going to be true that the central limit theorem approximately applies. And we can say this p1 hat minus p2 hat approximately follows a normal distribution. And we know its mean is the true p1 minus p2. And now its variance is the sum of these two different components. Now we can do our old trick again of subtracting off the mean and dividing by the square root of the variance to get a sort of complicated little fraction which approximately has a standard normal distribution. So this is good, and it allows us to maybe again think about confidence intervals and hypothesis tests. So let's start by looking at confidence intervals. Let's recall we know that this complicated little fraction is approximately a standard normal distribution. Now we have our usual problem that the variance here, the variance in the denominator, actually involves these quantities p1 and p2, which are unknown. So for confidence intervals, we can do our usual trick. We'll say, well, we'll approximate p1 by p1 hat and approximate p2 by a p2 hat. And then we can say, well, now we've got a 95% confidence interval just like before. Namely, we want a confidence interval for p1 minus p2. And, well, that's going to be given by p1 hat minus p2 hat plus or minus. And if it's for a 95% confidence interval, then we use 1.96 times the square root of this variance term, which in this case it's a little more complicated. It's p1 hat times 1 minus p1 hat over n1 plus p2 hat times 1 minus p2 hat over n2, but it's still just a formula, and it gives us confidence intervals. So let's try a simple example of that. Let's begin by recalling that we were talking a few lectures ago about some poll results for Toronto's mayor, Rob Ford, and there was a poll done in September of 2011 which said that his support had dropped compared to a previous poll. Well, the previous poll was in June of that same year, and here are the results. The number of people surveyed was 1,050 with his support at 57% in the first poll, and was 1,046 with his support at 42% in the second poll. So it certainly seems like there was a drop, but suppose we want to get a confidence interval for how much of a drop there really was. Well, the 95% confidence interval for this difference, his true support at the time of the first poll as compared to his true support at the time of the second poll, is given by the formula that we just developed. So it's the observed difference between the fractions of support plus or minus this 1.96 times this square root of this big complicated variance term. And well, it works out so the observed difference is 0.15 or 15%, but then plus or minus this uncertainty, which is about 0.042. And when you work it all out, it says that we can be 95% confident that the true amount of support drop that the mayor experienced between these two polling times was between about 10.8% and about 19.2%. So that's our conclusion. We say, yes, his support seems to have dropped by something in this range. For a second example, let's consider two polls that were taken to gauge the voting support of US President Obama just before the 2012 election. So in the first poll, they surveyed 1,010 people, and he was at 52% support. In the second poll, they surveyed just 563 people, and he was at 48% support. So in this case, his support went down a little bit, and the question is, does this mean there was an actual drop in his support, or was it just the luck of the polls that they did? Well, once again, we can compute a 95% confidence interval, and in this case, we can say, well, it's the observed difference, which is 0.52 minus 0.48, or 0.04, plus or minus this 1.96 times the square root of this big complicated variance term, and in this case, it works out to a confidence interval of between about minus 1.2% or positive 9.2%. So in other words, we can't really conclude much of interest. We can say that it's possible that his support actually went up a little bit, or it might have gone down by as much as 9.2%, but we're not really sure, and the situation is a bit unclear. And this leads to the question of whether we can test for whether these differences, like P1 minus P2, really are positive or really are negative or actually could be zero. So let's next think about hypothesis testing. So remember that in hypothesis testing, we want to test some null hypothesis as compared to some alternative hypothesis. In this case, if we're looking to see whether, for example, a politician's support has changed between one poll and the next, well, the hypothesis, the null hypothesis, would be that their true support stays the same, and the alternative hypothesis would be that there's been some change in support. Now remember what we know from general theory. We know that this funny thing, this P1 hat minus P2 hat minus the difference of the two means divided by the square root of this complicated variance formula is approximately a standard normal. Now, as with confidence intervals, we have the problem that P1 and P2 are unknown. But in this case, if we're testing hypotheses and we want to compute probabilities under the null hypothesis, we can use the fact that we're assuming then that P1 equals P2. And in that case, we would approximate both P1 and P2 by their pooled estimate, that is this P hat, which is the total number of successes in both samples divided by the total size of the two samples together. So with this P hat, we use that as an approximation for P1 and for P2 in the formula, and now we say that this other expression is approximately a normal 0, 1. It's just like before, but we've substituted this new value P hat for both P1 and P2. Now we can use that to compute p-values for hypothesis testing. So to go back to the example of the Ford polls, remember we had two polls with different sample sizes N1 and N2 and different observed proportions of successes P1 hat and P2 hat. Now, the question would be, is there really a drop in his support? Now, the confidence interval that we already computed for P1 minus P2 suggested that it was positive and therefore suggested that there was a drop. But a confidence interval is not quite the same as a hypothesis test, and we don't want to confuse the two, so we want to do a pure hypothesis test now. And we want to test whether P1 equals P2 or whether P1 is not equal to P2. Well, in our observations, we had P1 hat minus P2 hat, of course, was 0.15. So we observed a 15% drop in support. We also compute this pooled value for P hat, which works out to 0.495. And now we can say, well, the p-value should be the probability under the null hypothesis that we would observe a difference in P1 hat minus P2 hat, which was at least as big as the observed difference, which is 0.15, even under H0, which assumes P1 equals P2. Well, that probability, again, by subtracting and dividing and so on, we can rewrite it in terms of something involving the absolute value of approximately a standard normal distribution and saying, what's the probability that a standard normal distribution is bigger than or equal to this new value? And by the way, we didn't have to worry too much about subtracting P1 minus P2 on the right-hand side because we're assuming under H0 that that equals 0. Anyway, so it works out to saying what's the probability that the absolute value of a standard normal distribution is bigger than or equal to 6.87. Now, 6.87 is a very extreme value for the standard normal distribution, which we know is usually between -3 and 3. So we can say, well, that's an extremely small p-value, and we can thus reject the null hypothesis. And we can say, no, it's just not true that P1 equaled P2 in this case. It's not true that Mr. Ford's support stayed the same between the two poles. On the contrary, it really did change, and his support really did drop between the times of these two poles. What about the Obama polls? Well, in that case, remember we had two different polls with two different numbers of people sampled and two different observed proportions of the people who supported Obama. And now we can test, is there a drop in support? Well, in this case, again, we have the null hypothesis that P1 equals P2 compared to the alternative that they're not equal. Again, we can compute the observed drop, which is 0.04, and we can compute this pooled value for P hat, which is 0.506, or just over 50%. Then once again, the p-value should be the probability under H0 that we would observe a difference in P1 hat minus P2 hat, which is bigger than the 0.04 that we did observe. Well, again, we can subtract and divide and work through it and end up saying it's the probability that a standard normal distribution is bigger than or equal to 1.52. Well, that's not so unlikely. That works out to about 12.9%. And that's probably bigger than our significance level. So we can say, well, in this case, the p-value isn't too small, so we cannot reject H0. That means it's perfectly plausible that, in fact, Mr. Obama's support didn't change at all between these two polls, and that was just the random fluctuation because of the random sample that they did to get the poll. And that's what we say in this case. For a final example, let's go back to that study of the HPV vaccine and how it affects HPV infections. Remember that they had a large sample of 6,163 young women who'd gotten the HPV vaccine, and they found that only 23 of them got HPV infection. They also had a sample of 6,018 young women who got some other vaccine, and they found that 345 of them got infected. So the question is whether this allows us to conclude that this HPV vaccine is useful, and indeed how much did it affect the infection rate. So let's start by considering confidence intervals. Well, we know the drill now. For the confidence interval, we take the observed difference, which in this case is just 0.004, the fraction who got infected with the HPV vaccine, compared to 0.057 as the fraction who got infected who took the other vaccine. And then we take that plus or minus, well, if we're doing a 95% confidence interval, then it's 1.96 times the square root of this big complicated variance expression, which in this case works out to a confidence interval of between minus 5.9% and minus 4.7%. So this means that P1 minus P2 is negative. In other words, P1 is a fair bit less than P2, and indeed that indicates that the young women who got the HPV vaccine were indeed less likely to get HPV infection, and in fact, the incidence decreased by probably between 4.7% and 5.9%. So that's a very big decrease. We can also think about it in terms of hypothesis testing. And in this case, we'd again want to test the null hypothesis that the true incidence of infection was the same for the two groups compared to the alternative hypothesis that it's different. Well, we still have those same numbers for the number of people in the sample and the observed fraction of infections for the two groups. So we can again compute the difference between the observed fractions. And now for hypothesis testing, we can compute this pooled value p hat, which in this case works out to about 0.030. And then the p-value, as we know, is to compute under the null hypothesis, what's the probability that we would observe a value of p1 hat minus p2 hat in absolute value, which is bigger than or equal to the 0.053, which is the absolute value of the difference that we observed. And again, we can subtract and divide by the square root and end up saying it's the same as the probability that the absolute value of a standard normal is bigger than or equal to 17.14. Now, I don't have to tell you at this point that that's an absurdly extreme value for the standard normal, and indeed, the p-value that you would be bigger than that is so small it's unimaginable. It's like 7 divided by a 1 followed by 66 zeros. It's just a number that's too small for us to think about. So we certainly reject the null hypothesis, and in this case we can say yes, the HPV vaccine did indeed help in the sense that the true incidence of getting the infection was definitely and unquestionably less for the young women who got the HPV vaccine as opposed to those who got some other vaccine. Now, can we conclude from this that the vaccine actually caused the infection rate to be lower? The answer is yes, we can. Because this was a randomized study, it means that whatever relationship we discover must actually be a causal relationship. The vaccine is what caused the infection rate to be lower. So in this way, we can now understand how to study two different independent samples of proportions. We can compute confidence intervals and hypothesis tests for the difference, the p1 minus p2, even when the two samples are independent. Next, we'll consider how to do the same thing when we're considering means instead of proportions.